Hi everyone, I hope you are doing well. So in today's video, we'll go through the 2018 physics exam part 1, where we'll be going through short answer questions from question 1 till 10. And the other questions will be done in part 2. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. An electrical field accelerates a proton between two plates. The proton exits into a region of a uniform magnetic field at a right angle to its path, directed out of the page as shown in figure 1. So we're given the mass, the charge of a proton, accelerating voltage, distance between those two plates, and the strength of the magnetic field. Beautiful. Calculate the strength of the electrical field between these two plates. Beautiful. So I'm just going to have a look at the formula sheet. And so that formula is actually V equals ED. We use V equals ED. V equals ED. Where, of course, V is voltage, E is the electrical field strength. And that's what we want to calculate. So, of course, your electrical field strength is just voltage over distance. So, putting that in our formula sheet. So, V is equal to, what's our voltage? So, our voltage, in this case, is 10 kilovolts. So, that's 10 times 10 to the power of 3 to make it volts, and divided by its distance, which is 20 centimeters, which is just 20 times 10 to the negative 2 to convert it to meters. And so putting this in your calculator, we get 50,000. And so to how many significant figures? We're doing it to 2 significant figures. So I would write this as 5.0 times 10 to the power of, let me write the 0 nicely. 1, 2, 3, 4 to the power of 4 volts per meter. Beautiful. Calculate the speed of the proton as it exits the electrical field. Show you're working out. Beautiful. What other beautiful questions? Because what we know is we use the electron gun formula in this case. So your electron gun formula is half mv squared. So you should have all these from your textbook. These formulas, half mv squared is equal to your charge times your voltage. And so what we want to calculate the speed, the velocity. So we know to get that, so that will be 2q, so 2qv divided by m, and taking the square root of that, that should give us our velocity. I rearranged it, and so putting that all inside, 2q, which is the charge of the proton, 1.6, so 1.6 times 10 to the power of a negative 19. I want to double check if that's right. So times your voltage, which was 50 kilovolts, well, 10 kilovolts, so 10 kilovolts. So 10 times 10 to the power of 3 to get it to volts. All divided by its mass. So the mass of a proton is 1.7, so 1.7 times 10 to the negative 27. Beautiful. Is that? Just double check your answers. Beautiful. Looks good. So putting that in my calculator, 1.6 times 10 to the negative 19. 10 times 10 to the power of 3. So 1.7 times 10 to the negative 27. That gives me, to 2 significant figures, 1.4 times 10 to the power of, so 1, 2, 3, 4, 5, 6 to the power of 6 meters per second. Beautiful. That looks good. Question C. With a different accelerating voltage, the proton exits the electrical field at a speed of this. So we're given the velocity. Calculate the radius of the path of this proton in this magnetic field. Show you're working out. You should use this formula. You should know R is equal to mv over qb from the formula sheet. So this is going to give you your radius of the path. So your mass of your proton was 1.7 times 10 to the negative 27. Is that right? Beautiful. And so the velocity we're given, so it's 1.0 times 10 to the power of 6, all divided by the charge, which is just 1.6 times 10 to the negative 19, times your magnetic field strength, which is 2.0 times 10 to the negative 2. 2.0 times 10 to the negative 2. I'll double check that. That's it. So putting this in your calculator, you should get your radius. Making sure everything's right in the calculator. I'm putting that on. That gives me, to how many significant figures? Well, 2 significant figures, 0.53 meters to 2 significant figures. Beautiful. Question 2. A square loop of wire, 10 turns with a cross-sectional area of this, passes at a constant speed into, through, and out of the magnetic field of magnitude this. As shown in the figure 2, the loop takes 0.5 seconds to go from position X, so, alright, this is where the magnetic field, yep, so position X is here, to position Y, where now it's inside, fully inside the magnetic field. So, alright, that's your change in T. Looks good, and yeah. Calculate the average EMF induced in the loop as it passes from just outside the magnetic field to position X to inside the magnetic field at position Y. Show you working out. Beautiful. So from position X to position Y, there will be a change in flux. So remember your EMF is equal to your N. Well, we're not going to write, it's actually negative N because, but we don't care about N when we're just trying to calculate that EMF, the voltage. So it's just going to be change in flux over change in time. So your N is your number of loops. So the number of turns is 10. So 10 turns. Your change in flux, remember your change in flux is your area times your magnetic field strength. So what is our area? They've given it to us. So 1.6 times 10 to the power of 1.6 times 10 to the power of negative 3 times your magnetic field strength, which is 2.0 times 10 to the negative 2. Yep, 2.0 times 10 to the negative 2, all being divided by your change in time. And the change in time is, it takes 0.5 seconds to go from position X and Y, so 0.5. Putting that all in my calculator, I should get okay, so I get, to how many significant figures? Well, they'll all look 2, so it will be 6.4 times 10 to the power of, so 1, 2, 3, 4, to the power of negative 4 volts, because it's going the other way, yep. 1, 2, 3, 4. Beautiful, negative 4 volts. Beautiful. 3 marks. Sketch the EMF induced in the loop as it passes into, through, and out of the magnetic field. You do not need to include values on the axis. You would have had this question if you do past exams, a lot of past exams. This question repeats in every exam, I promise you. So it's one of the most nicest, easiest way to get full marks. And yeah, to do it like the EMF time graph, the best way to do it is actually first drawing and sketching the change in flux graph over time. So we're looking at loop outside the field, loop entering, loop inside, and leaving, and okay, beautiful. So let's first just draw a basic graph of how the change in flux varies over time. This is really going to help us kind of visualize. So this here is your change in flux, and this is your change in time. So say we start over here. Right over here. Well, okay, there's no change in flux. You know, initially there would be no change in flux because there's no magnetic field lines passing through it. And it goes and it goes and goes and it goes until it hits position Y. So imagine you're going from, no magnetic flux from here to here, around here, let's say, until you hit position X, which is this position. The further that you go now from position X, you're now going to get field lines passing through that loop, and hence we're going to have a change in flux. This change in flux is going to be increasing because as we're going more and more of the field lines are going to be passing until you hit Y, where now it's fully, the full loop is filled with magnetic field lines. So it's going to be increasing at a nice steady rate until it hits position Y, which is over here. And so, of course, now it's fully, magnetic field, the loop is filled with magnetic field lines, so there's going to be a change in flux. That change in flux is not going to change anymore. It's going to actually be kept constant because as we're going further, the whole thing is still filled up with, there is no change in magnetic flux. It's just going to be the same flux over, so it's going to have some constant value. Until it reaches this here, where now it's going to get out of that, magnetic field. So when it gets out of it, it's going to slightly get out, and the magnetic field is actually, the flux is going to start decreasing at a steady rate until now the whole thing is gone, and as it moves more further and further away, it will be then constant again, because there will be zero flux passing through it. And here is our graph of our change of flux over time. So I'm just going to take this here, because this is going to really help us draw our EMF. So copy that and really push it over here. All right. So like we said, so this part over here is the loop outside the field. And what can we see? Remember that the formula, your EMF is just negative n change of flux over change in time. Your change in flux is the derivative. This part here just means the derivative of this graph. So think of it like if you do methods, it's talking about the gradient. This here is the gradient. So of the line. So for example, here have a look at this part here, which is this part over here. We can see that the actual, it is constant. The gradient is 0. It's just a constant value. So the gradient here is 0. So imagine if the gradient is 0, if you put it 0 here, your EMF is going to be also 0. So we're going to actually have a straight line from here to here until loop outside. Until we hit position X, we can see now there's an actual increase in gradient. It's actually a positive gradient as it's going up. So remember, imagine we have a positive gradient. So this here is positive. But because we still have a negative, remember, Faraday's law, there's going to be a negative. So we need to, even though it's positive, multiplied by that negative, it's going to be a negative. So it's actually going to be below. So let me draw this over here. It's going to be below, like that, and move back up. So this here, it's going to be below. We're going to produce a EMF that's negative. Yeah, because, okay, we got, and it moves as at a constant value. The gradient is constant. So yeah, so here, as we can see, it's, sorry, here we can see that it is constant. And so again, here, now the gradient back is 0. Loop that's inside the field. Now it's again back to 0. The field line 0, so hence we're going to have an EMF that's actually just 0. And so then at the end of the thing, it's the gradient is going to start decreasing of the magnetic flux. So if this decreases, if this is a negative, and you're multiplying it by a negative, it's going to be a positive EMF. We're going to actually induce a positive EMF. So a nice positive EMF. And then as it passes out, of course, it becomes 0 again. So, and it moves like that. And that's it. So I think it's an ugly color, to be honest, how I drew it. So let me draw with a red. So this is how it will look. A very nice typical question in an exam. So make sure you know how to do it. It's very easy. And yeah. Like that. Beautiful. That's it. Next question. Question 3. Students build a model of a simple DC motor as shown. All right. The motor is set with the coil horizontal as shown, and the power source is applied. So will the motor rotate in the clockwise or anti-clockwise direction? And explain your answer. So this is a nice easy question. So because this is a positive terminal, we're going to have current coming out here. And so it's going to go pass through here, and in the H to G, the current's going to go from H to G. It's going to pass through here, it's going to pass through here, and it's going to come out to the negative terminal. So the main thing is have a look at H and G. Using your right-hand slap rule, remember you're using your right-hand slap rule, what is the force that's being produced? Because remember there is a magnetic field line's going to go passing from north to south, which is this way. So using your right-hand slap rule, your thumb is going to go towards the direction of the current, which is HG, and your fingers are going to go to the direction of the magnetic field, which is that. And so your hand, your actual palm, is the force that's going to be created, and that force is actually downwards in my case. So I'm going to rub this out, a little bit rub kind of this out, and so this here force is downwards. So we have a force that's being produced that is downwards. Force that's going to produce downwards. Beautiful. Now let's try to F and E. Remember, there's no force produced here because they are parallel to the magnetic field lines. Remember, when the current is parallel to the magnetic field lines, there is no force produced. So have a look at over here. Because now, okay, again, the magnetic field lines are perpendicular to F and E. Again, using your right-hand slap rule, we will find out that the actual force is upwards when we're here. So I'm just going to rub these out. Now the force is upwards. It's going to be a produced force on upwards. So if H and G is downwards and this is upwards, it's going to be turning this way, which is C, clockwise direction. So will the motor rotate C? So you just put C. and it will rotate in the clockwise direction. And we've kind of explained that just from this, so we're just going to write a nice statement through marker. So, all right, so what we're going to say is nice, easy. So from the figure, the current direction goes from H to G, and from F to E, all right, using the right hand slap rule on H and G, on H to G, the force is directed down, and F to E, F to E, so F to E, force up, hence clockwise rotation. That's it. So from the figure, the current direction goes from H to G and from F to E. Using the right hand slap rule on H to G, the force is directed down, and FE, the force is up, hence clockwise rotation. Pretty much a nice, beautiful explanation there, and that's it. Very simple. Yeah. Okay, one of the students suggested the slip rings would be easier to make than a commutator, and they should use slip rings instead. You should know this is a rubbish idea. You should never, ever do that, especially in a DC motor. You should never use slip rings. Explain the effects that replacing the commutator with the slip ring would have on the operation of the motor if no other change was made. So let's really understand what happens when you put a slip ring. What a commutator does, it kind of reverses the direction every 180 turn, every half turn, and so it keeps the direction, it keeps the rotation in the same direction. But when you replace it with a slip ring, this is where a problem happens. So let's really look at this. If we let's do this. So of course the current direction is the same, but if we replace it with a slip ring, imagine looking into the page. So imagine looking into the page here. So you're seeing this part over here. So let me have a draw at that. So you would have, of course, initially it's in the horizontal direction. So imagine this is your E, and this is your H. So you're looking into the page in this direction if you're in the eye view. And so, of course, the force is down on H, we can see, it will still be down. So I'm drawing a downwards force. And of course, on E, it's upwards. And so you can see that the rotation would be turning clockwise. Great. But the problem is using a slip ring, have a look at this. Using a slip ring, the forces are not changing direction, and I'll show you what that means. So imagine, okay, so what's going to happen is the coil is going to rotate 90 degrees. So when it rotates over here now, where now this is your H, and this is your E. And the forces are still upwards, by the way. The forces are not changed, those forces. So, of course, E is still upwards, and H is downwards. So have a look at this. So there's actually there's no rotation. You're going from here, and it's turning, of course, clockwise, because there is some torque. But when you reach this, it's gonna stop at the vertical position, because the forces are pushing up and down. There's actually no torque that's happening. Well, in real life situation, there is some torque that will happen. For example, if you moved it to right, there would be some movement still, like the positions will be like, this will be your E and this will be H, but still the forces are up and down. So this one's still up and this is down. And so you know what will happen? It will oscillate between the directions. For example, this will create, and then it will rotate anti-clockwise, and again, it will become, in this direction again. So it will be, then it again in this direction, and it's just going to oscillate between the positions, and at the end, it's just going to stop at the vertical position. And that's why it's useful to use a slip ring. It really does not create a continuous rotation. And yeah, so, but I think because this question is just 2 marks, to be honest, we don't want to talk too much about, if it was a 3-4 mark, it would make sense to talk about how it will oscillate between the vertical position. I think just the most basic, to get the full marks, you just need to say, just really include these, not this actually, just these here. You just want to say that it will rotate 90 degrees and it will just stop in the vertical position due to the fact that the forces are acting, are not changing. So the forces are not changing. So your forces are supposed to change like that. And so you still so you should have a continuous, but they don't change. So yeah, I think that's the most easiest way to get the full marks in this question. So explain what affects. So what the first thing you would just say is the motor, because it's saying what replacing the motor with slip rings will have operation. Okay, the motor will not operate properly. That's the first mark will come out. The motor will not operate correctly. That is your first mark. Of course, they won't operate, and we'll explain why. So, the motor will initially rotate 90 degrees clockwise and will stop in the vertical direction. Because, of course, in real life, this doesn't happen. It just kind of, because I've talked a little bit, there is still a force. And so then it will, of course, oscillate. But that, I think it's due to 2 marks, just explaining why it doesn't work and just saying that it will rotate 90 degrees and stop. I think you will get full marks for that. So I don't think you need to really go in depth with this question. So it will stop in the vertical position, direction, position, not direction. That's not a good way. Vertical position. Due to the force acting on the sides perpendicular to the magnetic field, not changing. And this should be full marks. I think that really does summarize everything. Yeah. Question 4. Let's have a look at this. All right. Figure 4 shows a simple AC alternator with the output connected to an oscilloscope and light globe. The oscilloscope can be considered as having a very large resistance. The coil is rotated as shown in figure 4. All right. Good. Okay. The output of the oscilloscope is shown, so we're given the voltage over time. Beautiful. The AC alternator is to be replaced with a battery. So remember, a battery is a DC. What voltage should the battery have for the light to light up with the same average brightness as it did with the alternator? What a nice, beautiful question. I think if students don't understand what RMS means. So RMS, whenever you use RMS, root means squared. That's what it means. But so whenever, for example, whenever we get a voltage diagram here, this voltage here is actually, like, for example, this here, the peak is volts. Is the voltage peak voltage. It's actually your peak voltage. And so this is like the peak voltage is normally for AC, but whenever we're doing whenever we want to take something, this voltage, and we want to convert it to in terms of DC, that's where we use the RMS notation. So that's where we convert it to RMS, because RMS means that it will operate the same, just with the same voltage. For example, here this voltage is only for AC. It won't work for DC. And for us to know what voltage that will still give the same everything, like it will give the same power and everything, for the light to work the same, we just want to convert it to a DC voltage. The way you do it is just writing as voltage RMS. RMS just means it's the same as voltage DC. It will give you the DC voltage. That's what RMS does. So we know that voltage RMS is just your peak voltage over your root 2. So let's write that down. Voltage RMS is equal to voltage peak over root 2. So your voltage peak we got was what? It was 4. So 4 over root 2. And so, yeah, that's it. So let's put that on our calculator. 4 over root 2. That gives me 2.8 pretty much. 2.8 volts. Easy. So the rate of the rotation of the loop is doubled. So imagine now it's quicker. So what happens is, you remember your period. Your period is the time it takes for one full rotation, this whole rotation. So if you double the rate, it means you're doubling the speed. It will take half the period for a full rotation. So your period actually halves. That's what happens whenever you get these kind of questions. It's one of the most common questions, by the way. All exams kind of have these kind of questions, so absolutely. So, all right. On the figure below, sketch the output that will now be seen on the oscilloscope. The original waveform is shown in the dashed line. Beautiful. So, well, the first thing that I would straight away show is what happens to the EMF. The EMF actually changes. Because remember, your EMF, which is your voltage, is equal to your N times your change in flux over change in T. And so because, your period is your time, so half the time, if you halve this time, your actual EMF doubles. You'll double the EMF. For example, if this is 4 volts, it will be 8 volts on both sides. So imagine this is your 8 volts here. So that'll be 8 here. Let me just draw these lines, and it'll be negative 8 here. So it will double. So we got that. And so, of course, you remember your period, we said it halves. So this is one period of rotation. Because it halves, it will be here then. So it means that for one cycle, it should be something like that for one full rotation. Yeah, now let's just sketch a nice part of it. So it will look like something like that, goes like that. Well, it's supposed to really look nicer, but I don't know why my cat fingers is doing it. It's not really being... Wow, it's actually quite a, what's happening here? Alright, so put that there, like that. And so I'm just going to kind of duplicate this for every rotation just to make my life easier, like that. Duplicate. Just because I want to make it nice looking. And I want to also draw one that, of course, is like that. Whereas it's not really not helping, actually. Why is this really creating some trouble for me? Okay, so fix this up like that. I'm going to just duplicate it, and it'll look like something like that. So, ooh, it's so bad. Why is it looking like this? And then I'll duplicate this, of course, look like this. Okay, this one looks very bad, to be honest, so I'm going to rub these out. I'm just going to duplicate this here. So it'll look like this, pretty much. Beautiful. This is much nicer. So here it is. This is how your graph would look like. Let's rub these parts out. And that's your actual how your graph should look like when you, double the rate of rotation. Beautiful. Question 5. Let's have a look at this. So a physics class is investigated the power loss in transmission line. A student constructs a model of a transmission system that they first set up the model as shown in figure 7. The model consists of a variable voltage AC power supply, 2 transmission lines each with 4 volts. So the total resistance 8 ohms. A variable ratio transformer, a light globe, and meters are needed. The purpose of this model is to operate 4 volts light globe. Okay. A variable ratio transformer is one in which the ratio of the turns in the primary winding to turns in the secondary winding can be varied. So, okay. The resistance of the connecting wires can be ignored. In the first experiment, the transformer is set up on a ratio of 4 to 1. Okay, so this here is 4 to 1. And the current in the transmission line is actually measured to be 3 amps. So this transmission line is 3 amps. The light globe is operating correctly with 4 volts RMS across it. Calculate the power dissipated in the light globe show working out. So first of all, I don't like these kind of, the way, it's really sometimes confuses a lot of students because there's too much information. What I try to do is actually try to summarize it in a kind of a circuit notation. For example, I know that our AC power supply can be just drawn as like this. And we know that, of course, so we also have... So, of course, your resistance, which in this case is your transmission line. We said it was 8 ohms from the question. And so it goes to actual, this variable transformer, which, let's draw that. It's your variable transformer. And then we have a light globe, which looks like that. Beautiful. So this is kind of a summarized way. And so we know this is 4 volts here. We know that the current that runs here is 3 amps. And so now, yeah, we also knew that the ratio was 4 to 1 here. 4 to 1. Beautiful. So let's do our calculations now. All right. Calculate the power dissipated in the light globe. All right. So to do that, what I would do is I would try to calculate the current in the secondary coil. So in the secondary output here. To do that, of course, we have the current in the primary, and we also have the ratios. The number of turns. So what I'm going to do is I know that current in your secondary is equal to the current in your, divided by your current in your primary, is equal to your N, your number of turns in the primary, over your number of turns in your secondary. So we want IS, we're not IP, your primary is 3, your NP, which is your number of turns in your primary, which is 4, and that is divided by 1. So your secondary, pretty much, your secondary, let's take this part here at the bottom here. So your actual secondary is going to be 12 amps. So that's going to run. So, oh, sorry, what am I doing? Yeah, 12 amps. That's going to run through this over here. 12 amps. And so now it's easy because remember this formula. Let me move this. Remember this formula over here. Power is equal to voltage times current. Because we know the voltage is 4 in the light globe and the current that runs through it, we just multiply this and we get the power loss. The power that's dissipated, sorry. So your voltage is 4 times your, your current. So 12 times 4, that gives me 48 watts of power that's dissipated. Calculate the voltage output of the power supply, show you working out. So we want to find now, let's take this back to this diagram and put it more down, right over here. We want to try to find the voltage in this power supply. What is the voltage? I think the most easiest way to do this is first find the voltage in this resistor or the transmission lines, which can be easily done because we have the current and we have the resistance. So we know by Ohm's law, voltage is current times your resistance. So, which is just your current's 3 times your resistance, which is 8/24. So it will be 24 volts. So this here takes 24 volts. Sorry. This resistor or your transmission line takes 24 volts of voltage. And so we just need to calculate how much the transformer, the primary section of the transformer consumes in terms of voltage. And that's easy because we know the secondary voltage. We want to find the primary, and we also have the ratio. So to do that, remember, so we know that voltage in secondary, so let's say voltage in a primary, voltage over secondary is equal to your number of turns in the primary over your number of turns of secondary. So your number of turns of primary is what we're trying to find, divided by voltage in the secondary, which is 4, divided in the primary, which is 4/1. Leaving us with 4 times 4, which is 16 volts in the primary. So it'll be 16 volts in that primary. So this part here, this here consumes 16 volts. Now, if you add these two up, this will actually give you your actual voltage output of the power supply, which is what? 16 plus 24, that's 40 volts pretty much. So your power supply, 40 volts. So it will supply 40 only volts. Easy. Calculate the power loss in the transmission line, show you working out. Easy. So let's take all this information let's come down more with it. So let's bring it down 4 more. Right over here. So that's easy because we now have the current and we also have the resistance. Remember that for power loss, it's equal to I squared over R. We know the resistance that the current that occurs in the transmission line is 3 squared times the resistance, which is 8. Putting this times 8, that gives me 72 watts of energy of power loss. Done. D. In a second experiment, the students set up the variable ratio of the transformer at 8:1. So let's rub this part out. 8:1. And adjust the variable voltage power supply. So, okay, now we don't know the voltage again. So that the light globe operates at 4 volts RMS. So it's still 4 volts RMS. Calculate the total power loss in the transmission lines in the second experiment. So, all right. I'm just going to rub some of these stuff with these. Like, these are going to be wrong, of course. We can't trust these anymore because now we've the power supply voltage is down. But, actually, look at the current here. The current here will be the same, and here's why. If we know the resistance is constant, remember the globe is going to have some resistance, and it's a constant value. And if we're still running at 4 volts, we know about Ohm's law, voltage is equal to current times your resistance. And so think about it. If your voltage is 4 and your resistance is constant, your current still must be 12. Your current hasn't changed. So we know this current is going to be that. So To be honest, all we need to do is find the current that is running through the primary section of this circuit. So to do that, again, we know that primary over current in your secondary is equal to your number of turns. So your number of turns is secondary over your primary. So your number of primary is what we're trying to find, IP, divided by your current in your secondary, which was 12, is equal to your 1 to 8. So your, yep, number of turns 1 times 8, yep. So it's just going to be 12 times 1 on 8. And so that gives me 1.5. So your current is 1.5 amps that's running through this transmission line. Actually, sorry, take this one out. Why am I still have that? Now it will run 1.5 amps. So again, remember your power loss formula, power loss equal I squared R. Your power loss is your current's 1.5 squared, and your resistance still 8. Putting that there. Times 8. We get 18 watts of energy that will be lost. Next question. Suggest 2 reasons why high voltages are often used for transmission of electrical power over long distances. This is one of the most kind of common questions you'll get in exams, and it's very common. It's one of the easiest marks to get. So we straight away know when we increase the voltage in those transmission line, what happens? We know, so if we increase this voltage in this transmission line, the current decreases. We know that the current decreases. And so if the current decreases, that's actually a good thing, because we will have, from this formula, power is equal I squared over R. We know if the current decreases, we actually get less power loss in this transmission line, which is actually a great thing. So that, I think, should get you 1 mark, because that's the most common answer that you will get in an exam. But because it's 2 mark, we need to there's actually an extra thing that I'll teach you today that will also you can put, and it really shows your understanding of electricity. So, all right. Another thing that we can talk about is that, so that will give you 1 mark. But another thing that we can talk about is, because you are using high current again, and so you know your current will decrease in the transmission line. This will absolutely increase the resistance. So it will actually increase, this will increase the resistance in the transmission lines. Remember from the formula, V equals IR. As we said, if your voltage is increased, yep, and so if your voltage is highly increased, the resistance is going to slightly increase too. And so that's actually a good thing, because we know that using if the resistance increase in the transmission line, we know there is actually a way we write this. We know that the cross-sectional area, so that if you have a wire here, and this is a wire, yeah? This is your wire, and so the cross-sectional area of the wire is actually inversely proportional to the resistance. What do we mean by that? So if we have a high resistance, it means the wire can actually be very small, because they're inversely proportional. So high resistance means that the wire can be very small. So having a high resistance gives us a small wire, which is actually good, because that kind of saves in cost efficient. You don't have to create big wires and all that kind of garbage. So it means that if you have low resistance means that you have high current. We have to actually make them big. We have to make them very thick, the wires. So the wires become more thick, and so that will just create more cost production. We have to, it will cost more, and yeah, it's not very good. So one of the things that we can talk about when you're doing these kind of questions is, we can talk about how the cross-sectional area is actually inversely proportional to the resistance. So having a higher resistance is actually a great thing, because it actually decreases. You can actually have smaller wires. And so let's talk about that. And the first mark, as we said, was by increasing voltage, current decreases, reducing power loss in the transmission line. Power loss in the transmission lines. Beautiful. So, and now we want to talk about the new concept that it's actually a great way. So, using a high voltage decreases current. this increases, so this increases the resistance because V equals IR in the transmission line. Transmission line. The cross-sectional area of wire is inversely proportional to resistance. Hence, having a higher resistance means using smaller wires. Which will be cost efficient, I know I've kind of mumbled a lot here, like I've talked too much, but I hope like this, of course this is one of the, of course like summarize it in very, simple detail. This is too much, I know, so you don't want to write this. This is too much, but summarize it in very good points to get those 2 marks. And yeah, this is a great thing they should know, that again, having a high resistance is inversely proportional. So resistance is proportional to the surface, the cross-sectional area of a wire. So having a higher resistance, meaning that we have a smaller area of, we can use a low cross-sectional area of a wire, which is going to be very cost efficient. We don't actually have to make big wires and, that create resources, and that's too much, yeah. Question 6. A ball of mass 2 kilograms is dropped from a height of 2 meters above a spring as shown in figure 8. The spring has an uncompressed length of 2 meters, alright? The ball and the spring come to a rest when they are at a distance of 0.5 meters below the uncompressed position of the spring. Using 9.8 newtons per kilogram as G, show that the spring constant K is equal to 392. Show working out. Alright, so to be honest, the only way I would know this is just whenever I see springs, the best way to do them is by using energy conservation. How? So, well, we know the ball at the top here is, so I will of course make this the surface, of course. I'll create this as the ground. Think of this as the ground. And so imagine the ball is at the top here. Of course it has gravitational potential energy because it is at some height, which in this case is just 2.5. We have, of course, gravitational potential energy. We don't have kinetic energy because it will be at rest. Imagine someone's holding it before he throws it. He's holding it. There's actually no velocity. So kinetic energy is 0. But also your spring potential energy is going to be 0 because there's no, you're not compressing a spring at that position. So that's also 0. Means your gravitational potential energy is going to be at its maximum value when you put it at the top. And so what happens at the bottom? Now let's compare that. Remember how the energy conservation, the total energy must be constant. So at the bottom, what do we know? Well, the gravitational potential energy will be 0 because remember we're saying that this is the ground. So it's at the ground, there's no height. So, okay, your GPE is 0. Your kinetic energy is also 0, as we said, because imagine pushing a ball and so it compresses the whole thing down, but at 1 second it will actually be at 0 velocity before it goes up. So also we know the kinetic energy must be 0. So all of the energy must be spring potential energy, and it makes sense because the spring is being compressed. So that should be a max. So adding all these two up, remember this here must be equal to that by energy conservation. We can make a formula. So let's do that. So we know that GPE max, which is mgh, well, is equal to your spring potential energy, which is half k change in x squared. So mgh in this case is what? So it's your mass, which is 2. G is 9.8. What's the height? It was actually 2.5. It's equal to half. K is what we want to calculate. Your change in x squared is how much it has been being compressed. We said it was compressed from here to here, which is just 0.5 squared. So calculating that, we get K is equal to, so 2, 9.8, 3.5. We get 2, 0.5 squared. We get 392. Beautiful. newtons per meter, which, yeah, it's just pretty much this here. So that's easy to calculate. Next question. Determine the acceleration of the ball when it reaches its maximum speed and explain your answer. All right, so we know whenever we deal with spring systems, one of the most important things is to have and remember, when we're reaching at a maximum speed, the maximum speed occurs halfway through the spring. For example, imagine this is where the ball is, and of course, here at the bottom, there's no, the kinetic energy is 0, so the velocity is 0. This is where the acceleration is at its maximum. Because it wants, so when you're at that 0 velocity, the spring, it has a very high acceleration that it wants to go up. And of course, at the top, it will have an acceleration also at its max, because it wants to go at the most bottom. It wants to go down. And so we know whenever we deal with springs that the acceleration is always halfway between that midpoint. So it's around this point here, where it's going to have the highest max. So sorry, your maximum speed. Think about it. If you put this ball here and you let it go, the maximum speed will occur midway through the spring before the spring lets it go. Right over here. This is where your max speed occurs. Max speed occurs. Speed, or its max kinetic energy. But the problem is, at that position, the actual force of the F net is actually 0, because the force of gravity is going to be equal to your force of spring. So force of spring. So imagine the ball is here at that position, and there will be a force of gravity and the force of spring, and they will be equal to each other, meaning that the net force is 0, because they will cancel out. So we know at its, okay, whenever you're looking at spring systems, one of the most important things is whenever we want to look at the maximum speed, the actual acceleration is 0. And that is for both. Whenever you're dealing with vertical spring systems, this is so important to know. So for any vertical spring system, which is in this case too, the acceleration is going to be 0 at its maximum speed. So acceleration 0. And because, so acceleration usually F as force of gravity, which is Fg, is equal to force of spring, which is Fs. This is very important. You guys need to remember. There is so many concepts that you need to understand about vertical systems, vertical spring systems, which, yeah, you should realize that, yeah, absolutely. Energy conservations, and remember that at the top and at the bottom of its motion, like the acceleration is at its max, and at the middle, where it's over here, because of the spring, this is where we have the highest, where acceleration is 0, because both the force of gravity and the mass are going to be equal to 0. Because they'll cancel out pretty much. Beautiful. Hope that makes sense. Calculate the compression of the spring when the ball reaches its maximum speed. Show you working out. Beautiful. We know at its maximum speed that the force of gravity is equal to the force of spring. So force of gravity is equal to force of spring. And so force of gravity is just mg. And your force of spring is just your k times change in x. And we want to find change in x, which is the compression of the spring. So the mass was 2. The, G was 9.8. Your K was 392. And change in X is what? So let's calculate that. We get, how many significant figures do we want to put it? 2, I believe, yeah, 2 significant figures. So 0.05 meters. Done. All right, question 7. A small ball of mass 0.2 kilogram rolls on a horizontal table at 3 meters per second, as shown in figure 9. The ball hits the floor at 0.4 seconds. After rolling off the edge of the table, the radius of the ball may be ignored. In this question, take the value of g to be 10. So we're taking 10. Calculate the horizontal distance from the right-hand edge of the table to the point where the ball hits the floor. So of course, when the ball hits the floor, it's going to go through projectile motion and it's going to hit the floor. And that's what we want to calculate, this vertical horizontal distance. And so you should remember, this is just projectile motion. So we know whenever we're dealing with the horizontal distance, this is your formula. Distance is equal to Vt. Well, of course, the horizontal velocity is always constant throughout the motion. So if we know that V is just 3 times your time, the time it takes for it to go hit the floor, which is just 0.4 seconds, we get the actual distance, which is just 1.2 meters. Calculate the height of the table, show you're working out. So we want to now calculate this height of this table. To do that is we just want to calculate the vertical displacement now. So let's do that. Well, we know that whenever we're looking at the vertical, there's actually no initial, your initial vertical velocity is actually 0 from the question. So U is equal to 0. A is equal to negative 10. Remember, not negative 9.8. They told us to use 10. And S is what we're trying to find. And also, what else? We're also given the time, which was when it hits the floor, it's 0.4 seconds. So the formula that comes to mind is S is equal to UT plus half AT squared. So S is equal to, because U is 0, you'll times it by T, so that will cancel out. It's just A is negative 10, and T is just 0.4 squared. So 0.5, negative 10, 0.4 squared. And that gives me 0.8, but negative, because of course it's downwards. So 0.8 meters. Done. To how many significant figures do we want to answer? Well, everything's 2, so 0.80, I would say. Easy. Next question. Calculate the speed at which the ball hits the floor. Show you're working out. All right. So we know that when it hits the floor, we're going to get this. The ball's going to hit like this when it hits the floor. So because we can break this down to its vertical and horizontal components, we know the horizontal component is constant. We said the velocity in the horizontal component is constant. But what about the vertical, vertical component? So the vertical component, when it hits the floor, that's what we can calculate, because we already know that U is equal to 0 in the vertical direction, A is equal to negative 10, T is equal to 0.4. Now we just need to calculate V. So the formula is just V equals U plus AT, and hence V is just, because U is 0, is just negative 10 times 0.4, which is negative 4. So it's just take the magnitude of that, just 4. So using Pythagoras theorem, we can actually calculate this velocity over here. So using Pythagoras theorem there, I've actually kind of done all the question over here. So I do want to kind of show working out, so I'm just going to put them over here. Like that. Okay, so I know this is 3, this is 4. Using Pythagoras theorem, so let's call this x. So it'll be just x is equal to the square root of 4 squared plus 3 squared, just 5. So this distance x is 5. And that's your speed. Your actual speed is just 5 meters per second to significant figures. And we do want to, I think, just because we want to show some working out extra, because it's 3 marks, we said that U equals 0, V is what we're trying to find out, A is equal to negative 10, and T is equal to 0.4. So we use V is equal to U plus A T 0.4, which is negative 4. And so that gave us our answer. Easy. Question 8. Two blocks A of mass 4 kilograms and B of mass 1 kilogram are being pushed to the right on a smooth frictionless surface by 40 newtons of force, as shown in figure 10. Alright, a very nice question. Calculate the magnitude of the force on block B by block A. Show you're working out. So, if you're pushing this block to the right, they're both accelerating at the same rate, 100%. Because imagine you're pushing it, they're both accelerating at the same rate. A is the same for both. And so, if you're pushing A is actually pushing on B, by the way. We're going to have a force that A is pushing on B. But because of Newton's third law, where you will have an opposite reaction force, B is actually also going to be pushing on A, which is just going to be negative F, because remember, it's going to have the same magnitude but different direction. It's going to be the opposite direction. And so, if we want to calculate the magnitude of the block B by block A, which is, this over here, this force. Calculate the magnitude on block B by... so it's this force, this force. The way that I would do this question is actually by... Because I know the forces are actually just equal. Both these forces are equal. I'm actually just going to isolate this system, this A. So if I isolate it, for example, if I isolate it here, imagine this here is block A. So this is block A. And so and just your block A. All right, so this is block A, and so you're pushing still with a 40 Newton force. So you're still pushing with 40 Newton force, and of course we're gonna also have that negative F coming this way. We're just gonna put it as F, because we're only isolating this part. Sorry, we're only isolating this part. So forget about this force over here for B, only that part. And so using your net force, so we know F net is the addition of both forces. We're going to take right as positive because it's accelerating to the right. So it's going to be just 40 minus F. And so your F net is, of course, your mass times acceleration. Well, the mass of A is just 4 times your acceleration, which we don't know is 40 minus F. So we just need the acceleration. To get the acceleration, what the best thing to do is actually put this mass as 1. So if you add these two forces, if you just add these two masses and make it a one box like this, the only force of 40 is going to be still being pushed on them. And so it's going to be a 5 kilogram mass now. So again, using your mass times F net is just mass times acceleration. So if I know F net is 40, because that's the only force that's being produced, and the mass is 5, acceleration is just going to be 8. So if we know acceleration is 8, we put this in here, minus F, hence your F is just going to be 8 newtons. And yeah, that is going to be your force, 8 newtons. You can also do the same to isolate the other system. For example, what about if we forget about this one over here and we isolate B? As we said, B had this force over here. So if I just did the same for B, and this is the only force that's being produced, which is F, I'm going to use, of course, F net equals MA. So F net, the only force that's acting is F. So F net, which is MA, which is, of course, mass times acceleration, which is 8, is equal to F, and still the same force. So it depends, it doesn't depend, the system is going to be the same for. You can choose any system, by the way. So we get 8 newtons. State the magnitude and the direction of the force on block A by block B. So we're actually trying to calculate this force over here. So on block A by block B. So again, Newton's third law, they're going to be the same magnitude but in the opposite direction. So it'll still be 8 newtons, but in the opposite direction, which is left in this case. Easy. Question 9. This spacecraft Juno has been put into an orbit around Jupiter. The table below contains information about the planet Jupiter and the spacecraft Juno. Figure 11 shows gravitational field strength as a function of distance from the center of Jupiter. So we've also given the mass of Jupiter, the radius of Jupiter, and the mass of Juno spacecraft. And we're also given the gravitational field strength and the distance of Jupiter. All right. Calculate the gravitational force acting on Juno by Jupiter when Juno is at a distance of 2.0 times 10 to the power of 8 meters from the center of Jupiter. Easy. So we're just using this formula, Fg is equal to mg. We can easily calculate the g value at that position of 2.0 times 10 to the power of 8 from the formula, from the graph, which is what? So we know that g value is 3. So it's just going to be your mass of Juno, which is 1,500, was it? Yeah, times your g value at that position, which is 3, which is just going to give me to 2 significant figures, because I think everything, yeah, is it 2 significant? Yeah, no. Yeah, to 2 significant figures, that's going to give me just 4.5 times 10 to the power of 1, 2, 3, 3. Done. Use the graph in figure 11 to estimate the magnitude of the change in gravitational potential energy of the spacecraft Juno as it moves from a distance of 2 times 10 to the 8 to a distance of 1.0 times 10 to the power of 8 from the center of Jupiter. So we're going from 2 to 1. So imagine 2 to 1. That's easy. Remember, to calculate, when you're using a gravitational field strength versus a distance, you're going to have to calculate area under the graph at those positions, and you're going to have to multiply by the mass to get the energy, or the change in gravitational potential energy. To do that is we're just going to have a look at 1 square. What is the area of 1 square? Well, we can see that here, this is 1, the length of this is 1, and this here, the length here is just 0.5, and make sure it's times 10 to the power of 8, because that's the length of 1 square times 10 to the power of 8. So the area is just 1 times 0.5 times 10 to the power of 8. And so I got a big number, of course. And so now what I can do, just to put that number here, so it's just going to be 5. In other words, let me write it down. So it's actually just 0.5 times 10 to the power of 8. So the area of 1 square. All right, so that's the area of 1 square. And now we're just going to calculate how many squares there are. And let's do that. So we can say that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, including maybe this one, 11 including this one, 12, including that one, 12, 13, including that one, and say around, yeah, like 14, pretty much 14, around 14, or 13.5, any of these, 14, in this case. Let's say there's 14 squares. We counted 14 squares, so this is going to be 14 times the area of one square. That's going to give me times 14. That's going to give me just 7.0 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 to the power of 8. But remember, this is not energy, by the way. It's pretty much joules per kilogram. Joules per kilogram. To get the actual energy, you have to multiply by the mass of Juno. So at the end, energy is going to be 7.0 times 10 to the power of 8 times the mass of Juno, which is 1,500. So times by that, we get finally 1.05 times 10 to the power of 12 joules. So let's write that. Easy. Question C. Europa is a moon on Jupiter. It has a circular orbit of radius this around Jupiter. Beautiful. Calculate the period of orbit of Europa. Beautiful, nice and easy. So this is an application of Kepler's law. So I'm just going to pull out the Kepler's law formula. So Kepler's law formula is right over here. I'm just going to write it down. And I'm going to have to transpose it to period. So r to the power of 3 t squared is equal to gm over 4 pi squared. So if I reciprocate both sides, so just switch them around, flip them around, so 4 pi squared over gm. Multiply both sides by I to the power of 3, so I get, just if I square both sides, so it'll be just, I can get rid of everything, so square root also that, so 4 pi squared I to the power of 3 over gm. This formula here gives you the period. And you should have it in your formula sheet, to be honest. And make sure it's all transposed. So I think the best thing you should do in an exam is put the transposed formula in your thing for both the radius, the mass, and the period. Because it does take some time in the exam, and every time matters. So make sure you have it transposed. So this is the formula for the period. So let's write that down. The period is equal to the square root of 4 pi squared r to the power of 3 divided by gm, which is equal to, let's write that down, so 4 pi squared r is the radius, the orbital radius, which is 6.70 times 10 to the power of 8 to the power of 3, all divided by your g, your gravitational constant, which is 6.67 times 10 to the negative 11, times your mass, your central mass, which in this case is Jupiter, and they've given us the mass of Jupiter. Where is it? 1.9, so it says 1.9 times 10 to the power of 27. Is that right? Just want to double check it. All right, looks good. And so putting this in your formula sheet, so putting this in your calculator, 4 pi squared times 6.70 times 10 to the power of 8 to the power of 3, 6.67 times 10 to the negative 11, 1.19 times 10 to the power of 27. Entering that, I get to two significant figures. Everything was in two significant, was it 3? Everything looks like it's 3 significant figures. Yeah, so 3 significant figures, I get 3.0. So yep, 3.06 times 10 to the power 1, 2, 3, 4, 5. To the power of 5. Does that look right? 1, 2, 3, 4, 5. Yep. So I get 3.06 times 10 to the power of 5. That looks good. No mistake. Because these are the most dangerous kind of questions, because you'd easily make a mistake. So just have a look again at your calculator. Have you written in your calculator before moving on forwards? And yeah, that looks good. To the last question, which is 10. Let's smash through this question and get it over and done with. Members of the public can now pay to take zero-gravity flights in especially modified jet aeroplanes that fly at an altitude of 8,000 meters above the Earth's surface. A typical trajectory is shown in Figure 12. At the top of the flight, the trajectory can be modeled as an arc of a circle. Calculate the radius of the arc that will give the passengers zero gravity at the top of the flight if the jet is traveling at 180 meters per second. You might think, what? Zero gravity. And so that doesn't make sense, because remember, when they're saying they're feeling gravity, this is not true. They don't actually have zero gravity. So if I really zoom in here into this picture over here of when they're like flying, so it looks like that, and then it looks like that. Okay, so when the passenger inside, say you have a passenger inside, the only reason they feel like they're having zero gravity is when the plane goes up and goes down, you start a little bit levitating. So your normal reaction force becomes zero, because you're not in contact with that floor anymore. And so you feel like you're levitating. But remember, you still have your force of gravity. Your force of gravity is still acting downwards. But your normal reaction force becomes zero, so you feel like you're levitating. And you might think, oh, this is zero gravity. But remember, that's rubbish. Gravity, that's not zero gravity. So I think that's why they actually might believe that, oh my God, I'm actually levitating and stuff. So absolutely, that's not the case. It's just that your contact force between you and the floor of the surface is actually zero. And so you do feel like you're levitating and feel like you're having zero gravity. So beautiful question. So let's now calculate the radius of the arc. Well, the most easiest way is, okay, let's just draw all the stuff. So we know, of course, we have a force of gravity. Just force of gravity. Of course, the net force is downwards because we're down the arc. And also, we have a normal reaction force, which is zero. So which is, normal would be upwards, but because of zero. So that's what would happen. So we know that F net, let's write that now, F net is equal to, because we're taking down as positive, because that's where the net forces is, it's just going to Fg minus n, where n would be in the top. But because n is zero, we don't even worry about that. Cancel that out. Yeah, F net's, of course, mv squared over r. And Fg is just mg, so you can cancel out the m's. You get v squared over r is equal to g. And so v squared over g is equal to your r. So the radius can be actually calculated using this formula here. So r, so what's your velocity? It's just 180 squared over your radius, with your g value, 9.8. Let's get that. So writing that gives you a big number, but I want to make sure it's into 3 significant figures, the smallest I've used here. So 3.31 times 10 to the power of 3 meters. Beautiful. Next question. Is the force of gravity on the passenger zero at the top of the flight? Explain what zero gravity experience means. Yeah, this is what we just explained. The force of gravity is not zero. 100%, it's not zero. It's the normal reaction force that's zero. And so that's why they feel that sensation of zero gravity. So, no. The passenger force of gravity is not zero. So it's not zero. Zero gravity experience. So zero gravity experience means the normal force is zero. The normal force is zero. And this sensation creates zero gravity, experience. That's what it means. Very nice question. So no, the passenger force of gravity is not zero. Zero gravity experience means that the normal force is zero, and this sensation creates zero gravity experience. That's it. That should give you the mark there. And I hope you learned something through this one, and that's the last question. Part 2 will come in next time. So part 2 is going to go through question 11 till 20. And yeah, guys, please keep updated. Please make sure to like and subscribe. And like always, guys, I hope you guys have a great day and take care of yourselves. Bye-bye.